Today we have Sudipta Sarkar from IIT Gandhinagar. We'll talk about light rings of stationary spacetimes. Over to you.
Thanks, Disha. So I will let me begin by thanking the TFR group for inviting me and giving me this opportunity to present my work. So this work is done in collaboration with our PhD student at IIT Gandhinagar, Rajesh, and this is the reference of this work. So basically, I'm going to talk about theory of light rings and the general relativity of light rings, but I have to begin with certain observational features where obviously my expertise is very low. Okay. So all of us have seen this iconic image, and this image is the image of the supermassive compact object at the center of the M87 galaxy. It's a megaparsec distant galaxy. It's a remarkable technological achievement. And this image is taken at several telescopes. Okay, so you take images at different telescopes, bind the data, and ultimately this image pops up. And it at the wavelength of 1.3 nanometer, which is roughly infrared image. So size of the image in the sky is about 42 micro-arcsecond. And I mean, the resolution is remarkable. When you think of the sun is like half a degree, this is 42 micro-arcsecond. That's what the resolution we could achieve now with modern technology and software power. And the central depression in brightness is a flux ratio of 10:1. It means in the CCD camera, the central region is 10 times less, have less number of photons compared to the brighter region. Okay. And the obvious question is, what is the central object? I mean, that's like the $1,000,000 question. What are we looking at? What image it is supposed to be? So if you look at the EHT collaboration paper, they're being very careful, and they said that overall the image is consistent with the expectations we have for the image of a rotating black hole as Kerr's solution as predicted by general relativity. But nevertheless, there are several non-black hole candidates producing the similar image. For example, one could have what is called the horizon-like ultracompact object. I will define what do I exactly mean by ultracompact as I go along. And there are crazy alternatives like Rava star, Ozone stars, and whatnot, and its possibility of decade singularity, which is a little bit more exotic. I mean, there is a level of exotic. This is probably exotic square. And then if you look at the citations of the Nobel Prize in Physics 2022, and then you'll see that the Roger Penrose citation for Penrose, there's a clear mention of black hole. Okay, the discovery of black hole formation is a robust prediction of general relativity. But for Genzel and Gaze, the Nobel Committee is careful, and you see that what they say is that discovery of a supermassive compact object. Okay, I mean, that means the data is completely consistent with black hole, but nevertheless, there are other possibilities exist. There's a degeneracy in interpretation. Okay, that's what the situation is. So what do we learn from these photos? And these are remarkable photos. First of all, what we learn is the remarkable accuracy of general relativity. That's the first thing we learn. So for example, consider this table, which I have taken from EHT paper, the first paper of EHT collaboration. So what this table does is that this is for M87 case. It gives you the values of an angle, theta g. So this theta g is kind of opening angle. Suppose d is the distance from the source. This is like gm by d divided by c square. And from which you can estimate the mass of the objects. Okay. So there are these different models, GC filter, model fitting, image domain, future extraction. I don't know much about them, but the last two I know, the gas dynamics and the stellar dynamics. This is basically look at the X-ray data of, and also the gravitational, the optical data from the motion of the stars of these different galaxies. And then you estimate the mass. Okay.
Sorry, Sudipta, I missed what theta g was. Could you say it again, please?
Theta g is an angle which is gm by capital D divided by c square, where capital D is the distance from the source and m is the mass of the source. So they define
distance to us from the source?
From us of the source, capital D.
Okay.
So then if you look at this.
Sorry, so this is roughly the angle that that the event horizon of that mass would subtend.
I mean, let's not call it event horizon, call the object, what we see in the sky. Okay. Because what you see is actually the light ring, which can be a little bit larger than the event horizon. So
okay.
Therefore,
yeah, but what confused me was that you were defining theta g in terms of the mass. You were saying gm by d.
Gm by d and into c square. That's the way they define it, because this angle they can measure. And then from there, they can infer the mass.
I see. So they measure the angle and they
infer the mass.
so
Provided we know and reasonable estimate of the distance, which probably they have.
But suppose, the black hole was totally wrong. Suppose the size of the object was 1,000,000 times GM, then they would be measuring the angle, the mass wrong, right?
So what it turns out, that is what probably the point I'm trying to make, that if you look at the mass measurement from various models, which does not use this image,
I see.
and look at the mass of this image, which is measured from modeling it as a curved black hole,
I see.
then it matches remarkably. This is the 2 point, the 3.8 and 6.5. So it's clearly seen that the measurement of the mass is completely inconsistent with what is obtained from the completely different models. So, and for our galaxy also, there are mass measurement available. For example, astronomers have been looking at this motion of the stars around the central object, and there is this particular star SO1 and SO3 and other stars also. These motions have been observed for over years, and assuming a Keplerian orbit, you can estimate the central mass, and this stellar dynamics gives you a mass roughly about 10 to the power 6 solar mass for our galaxy. And the recent paper for the shadow observations also gives you a mass which is roughly same. I mean, not roughly, I would say very good agreement. Okay, given the uncertainties in the data, this is I would say very good agreement. So this immediately signals that we are confident what we are doing. We understand at least a major part of it, and the observation is well described by curve geometry. Okay. Although the rotation of the curve metric really does not play much of a significant role, at least for shadow observations.
I have a question.
Yeah, please.
Yeah. Why is the stellar dynamics and gas dynamics estimates very different?
I actually don't know. Okay, I think what happens is that the gas dynamics probably comes from the X-ray data, and maybe in estimation of different data, there is some systematics there. I don't know exact answer.
I see. Okay, thanks.
But my guess will be it is in the systematics of the observation what you do.
Okay, thanks.
Okay. So with this thing that we will define, so all these observations are based on a notion what we call a light ring. I will define light ring rigorously, but just to begin with the introduction, that you can think of this object and there's a background source of light from which a star, for example, from which light is coming. If the object size is much, much larger than the Schwarzschild radius of that object, then okay, some light bends and it comes back to us. Let's say sun, for example, you have the simple bending of light, which we understand. But if the compact object radius is relatively smaller and particularly smaller than a threshold value, we will come back to it in the accurate description of what this value is. And then we call it the ultra-compact object. So basically the ultra-compact object, there exists a circular null geodesic outside. So for example, when background light come, and it can go for circular orbits around that object. Okay. And this circular null geodesic, we will see that if there is an light goes inside this circular null geodesic, then it can go into the black hole, or I mean, it's like an unstable base. So it can either fall into the black hole or it can come out to us as a scattering orbit. First thing to important emphasis is that we all know this, the existence of a light ring does not imply that the central object is a black hole. And we know this famous example of Schwarzschild, the light ring as 3m. So suppose hypothetically, we can create an object of 2.5 mass as the radius. Well, how do you create that object is a not easy thing from the gravitational collapse, but suppose you can, then this object will have a light ring, but will not have a horizon. So let me emphasize that. Good. So the question for observational is that given this image, okay, how do you know observationally that this, or even theoretically, that what are you looking at? Are you looking at an ultra compact object with a light ring, or you are looking at an honest to God event horizon? Okay.
So Sudipta, sorry, a very stupid question. Suppose I had light coming straight, meaning from infinity past the black hole at some impact parameter B measured from infinity.
Yeah.
If that B is smaller than 3m, will that light end up inside the black hole?
So if it is smaller than 3m, then it will be cached into the black hole. It will go and go into the black hole. If it is larger than 3m, it will have a scattering orbit and it will come back to me. the observer.
Yeah.
But if it is a 3M, then it depends on the perturbation. You can either go out or it can fall into the black hole. That's the idea.
Okay, thank you.
But remember that if nothing happens for radial light ring, the radial light rays directly can go into, and radial light rays can also come out. Okay. Radial light ray, there is absolutely no problem. In fact, they don't see any potential in short shell orbit, in short shell spacetime, the radial light ray. So what I'm talking about, light rays which are not radial. Okay.
Yeah. So roughly speaking, the shadow, the Schwarzschild black hole would have a shadow whose size is 3M.
3M, but because of the bending of light, because I am at a distance, there is a √3 factor which just added to it. That's all.
Yeah, thank you.
You expect light rings to be in any plane?
Okay, that's a good question. Maybe I'll come back to this. This is a very important question. For Schwarzschild black hole, because of the spherical symmetry, things are very easy to define. But once you have a curved black hole, you know that equatorial plane has a very special character. Apart from the equatorial plane, the null geodesics are not confined in a single plane. Then what we call, they move along a spherical null geodesics. And then the situation is a little bit complicated.
Not necessarily closed even, or?
They will close, they will move on a surface. So then instead of a light orbit, it's better to talk about a photon region,
Okay.
a finite region. Good. So the question is that, does our horizon-like compact objects have a light ring? Is it guaranteed that if I give you a compact object, it's always have a reasonably compact, it will always have a light ring itself? Even you can ask this question, does all black hole solutions, irrespective of whatever theory or you are choosing, have a light ring? Of course, we know that curved black hole has a light region. Schwarzschild black hole, of course, has a light ring. But what about other crazy black hole solutions? Just by black hole boundary condition at the horizon at some asymptotic conditions, am I be able to say that whenever there is a horizon or whenever there is any other feature, there is a light ring outside? And this is exactly what we have proven, that any axisymmetric, stationary, asymptotically flat spacetime, these are the assumptions I need for the proof in 3+1 dimensions. These 3+1 dimensions can be relaxed. Okay. And the claim is that there must be at least one light ring outside the Argo region. So what we are saying is that if there is Argo region with this kind of assumptions put in, there must be a light ring outside. Okay. So it means that it does not necessarily have to be a black hole. As long as the rotating object is compact enough to have an Argo region, it will have a light ring outside. That's the claim. So if there is a horizon, I will argue that one can show by an argument that if there is a horizon, there must be a light ring outside. There must be a Argo region outside. And then by our theorem, there will be a light ring outside. Okay. This proof does not use Einstein's equation, does not use in energy conditions. It just uses the kinematical structure of the null geodesic equation in this background, and therefore is sufficiently general. Okay. So let me go ahead. And
Sorry, I missed what you said about the stability.
Hello, Vijay.
I missed what you said about the stability of the light ring.
So basically, the light ring, let's say Schwarzschild spacetime, the light ring is at the maximum of the potential.
Yeah.
So that's like what we call is an unstable light ring. So therefore, think of a null geodesic exactly at r equal to 3m. If there is a little bit perturbation, it can either fall into the black hole or it can go up to the infinity. So therefore, we call it an unstable light ring.
So all such light rings are unstable, right? All light rings are unstable.
No. This is a good question. So it turns out that this is a very important question. So what we can only prove that there is a light ring. Whether the light ring is a stable and unstable depends on whether there exist horizons. It will turn out, and these are many works going on, that if there is a horizon, outside light ring will be an unstable light ring. But if there is no horizon, the boundary conditions will require one of the light rings to be stable light ring. Stable light ring means minimum of the potential.
I see.
And if such object exist that with a minimum of the potential, they are bad. Bad in a sense, they are stable light rings are unstable under space-time perturbation. Okay, and that's the claim which Cardoso has made, that if you have light rings without horizon, you will see that space-time perturbations will ultimately destroy the object. So that means theoretically, the only black holes have light rings which are unstable and therefore better. So I'll elaborate these points later.
Okay.
So let me start with what is a light ring.
The question.
Hello.
Yeah, the question is, have you defined what do you mean by an ergo region?
Okay, so I will definitely define what do you mean by ergo region, but basically the ergo region, the way it is defined is that suppose I have a stationary solution, since I'm working with a stationary solution, which will have a time-like killing field. Okay, so ergo region is the place where the time symmetric vector has a zero norm, which is exactly what we do it for curved black hole. So basically it's a static limit surface. Hello, is that clear?
So on that surface, does it mean that light rays go in, are confined to that surface or something like that?
No, this is not a null surface. Ergo region is not a null surface. Think of what happens even for a curved black hole. A curved black hole, there is a null vector, which is, there is a killing vector, which is 1, 0, 0, 0, which is basically the time translation killing vector. That vector has a zero norm on a surface, which has some complicated r equal to m plus minus square root of m square minus a square cos square theta. That is not a null surface. That's a time-like surface. But there exists another null vector, another killing vector, which goes to zero inside, and that's the horizon. So what is happening is that in curved black hole, there is a surface after which there is no static observer. There can be a stationary observer, a constant distance from the black hole. But horizon is a place where there cannot be even a stationary observer inside. You have to fall in. So ergo region is the limit of the stationary observer. For Schwarzschild spacetime, the ergo region happens to be at the same place at the black hole horizon. So curved black hole, they are separated. That's why we have, for example, the Penrose process.
And for ultra-compact stars?
So ultra-compact stars, there are examples of ultra-compact stars with ergo region. Okay, there are some exact solutions. Okay, but if they don't have a horizon, so basically inside the ergosphere, there is a hard surface. That's the model. Is that clear?
Okay. Yeah.
Okay. So let me go ahead. So this is the potential. So this is the potential of the null surface, which a null particle sees outside a Schwarzschild black hole. And Schwarzschild black hole things are very easy, and you can clearly see the effective potential vanishes. L is the, by the way, the angular momentum. If the effective potential vanishes, if there is no angular momentum, so that means the radial light rays don't see anything. They just go out and in. Okay. But if there is angular momentum, then the potential kicks in and there is a maximum of the potential, and that maximum happens at r equal to 3m. Okay. And this is what we call a unstable circular light orbit. And you can clearly see that at r equal to 3m, you can show that both r dot and r double dot, this is with respect to the proper time. I should not say proper time because it's null geodesy with respect to some parameter. This is a circular orbit for allowed by the geometry. Okay. This is what we call the light ring. So this is what heuristic picture for the light ring. So there is a source and there is an observer, and light coming from the source to observer. In some sense, if the impact parameter is less than the 6m or 3m, then this light ring goes into it and ultimately hits the horizon, go into the horizon. Okay. Again, note that Schwarzschild light ring is unstable. It corresponds to the maximum of the potential. So light ring decides what I see in the sky. Okay, so this is a very interesting, pedagogical paper. A lot of people have defined this. So this is the angular size of the shadow. What I should see if there is a black hole is illuminated by the background. Okay, this is for spherically symmetric case where things are easy to understand. So this formula is actually probably first time derived by Sinch, and this is given by this formula. Okay. So you clearly see if you have very, very far distance from the black hole, that means your R0 is the observer point. So if R0 is much, much greater than black Rm, then sin theta is almost equal to theta, and you have the radius of the shadow is equal to 3 root 3n. Okay. So basically, if you're far distance, infinite distance away from the object, what you should see is a black spot of radius 3 root 3 into mass. This root 3 is the exactly what it signifies is that there is a bending of light. Otherwise, you could have only see 3m. Now, if you move closer and closer to the surface, the size of the shadow will increase. Okay. So if you are at the light ring at r equal to 3m and you're looking at that object, half of your sky will be black. You go inside more and more, and the sky will, the black portion will, what should I say? It's more of eating the entire sky. And ultimately, when you're very close to the horizon, the entire sky behind you become black. Okay. So this is the way, at least for spherical symmetry, how your observations is how you see the black hole. If so, the model is there's only one spherically symmetric black hole, Schwarzschild black hole. Behind there is a background is led by the backgrounds. Okay, I think there is a question.
Hello. How to define light ring for binary objects? Just like
Good question. The answer I don't know, because this, first of all, the binary things, if they are unstable, okay, then they are not even stationary. Okay, then all these constructions are, goes out of the window. So I don't know how to do it for binary. And symmetry is not also there. We don't know the solution. We don't know this is not even an axisymmetric configuration. And we don't know basically how to define even for generally stationary black holes, it's very difficult to define the notion of light ring and shadow. And I will come back to that. Is because the null geodesic equation need not be integratable. Okay, so for example, in curved black hole, we have a very special symmetry, the existence of Carter constant. Therefore, I could able to convert the null geodesic equation into first order differential equation. Things become very simple. I should not say very simple, but rather simpler. So I don't know how to do it.
Sudipta, I didn't quite understand what the shadow is. I mean, it's a projection of the light ring in the celestial sphere. What does this mean exactly?
Okay. So what happens, so let me define it carefully. What happens is that you have the light ring. Then what you do is that you define what is called, in some sense, you can say that if the light is coming from the light ring to you, okay, then how do you project the entire light to the background celestial sphere? This is done what is called using what is called a celestial coordinates. So basically you think of you are at an infinite distance and there is some coordinate on a two-dimensional sky, so alpha and beta. And how does the locus of the light ring you see in terms of the celestial coordinate, and that you define as your shadow. That's the definition of the shadow.
Yeah, isn't it that if you take the last bit of light that's come to you, it comes in a straight line to you and you project it backwards.
Exactly. So what do you do? Technically speaking, you put a tetrad at your place. You know the background spacetime, take the tetrad backward to it, follow the light path exactly, and create the contour around it in terms of the celestial coordinate. That is exactly
projected backwards in just a straight line. Imagine this flat space.
Flat space.
Yeah. So because of the bending, you get this extra
root 3 you get because of the bending. Otherwise, you would have got completely 3n. So that projection in the background sky is called a shadow.
So first of all, why is the light coming to me from light ring? I thought light ring is some closed orbit.
So what is happening is that this is the background. So you think of the bulbs outside, behind the screen. So this
should I think of the light ring as a boundary between the region which sucks in light and which lets the light out?
So to be more precise, in some sense, yes, but I want to be a little precise. If there are background light which is coming towards you, light ring is basically the boundary which determines the boundary of the shadow in the projection at the sky.
Yeah, I think I understand. Thank you.
Sudipta, what is the source of this light?
Background stars. Background stars.
Background stars behind
it. Yes. Okay. And also the emissions. For example, there could be nearby emissions and everything all together.
Yeah. What about the matter that's accreting around the black hole? Isn't that
okay? Shiraj, to answer that questions, what you have to do is that this is actually, so this is a theoretical model. When you actually look at the what is happening in the actual image, what they do is that they take this background general relativistic null geodesic solutions, and on top of it, they add the accretion models. That means the dynamics with magnetic field and whatnot, okay? And then solve the system together. Okay. So basically you understand that, okay, now I have this null geodesics in general relativity, but if I put matter, how does this null geodesics get affected? This part is entirely done by modeling, and then the final image comes out.
Right, but isn't that matter a significant source of the light that you're seeing?
Absolutely, absolutely. So this is only an ideal condition. So the image you see, in fact, this is also a part of a lot of debate in the GR community. If you look at the people like Wald, okay, they have written recent papers saying that why you call it a shadow, because the dominant contribution in that light is also coming from the accretion. Okay. So in the actual picture, what we see in the Event Horizon Telescope, there's a lot of contribution from the accretion light also, and the radiation also, definitely.
So, Sudipta, for this shadow, I mean, in order to have the shadow, it's not necessary that the light ring is stable or unstable, right? It's just a matter of light falling inside.
In fact, probably observationally, at least as a picture, you will not even see the difference. Although now there is really recently there is a paper which says that in terms of other more subtle feature, there could be a difference in terms of the stable or unstable shadows, but overall pictures you should not even see a difference. Should I go ahead?
Sorry, just one more question.
Yeah.
Suppose the accretion disk was sort of like this, side on. Fine. But suppose the accretion disk was straight on.
Okay.
Then because this part of the stuff that's accreting is right in front of the black hole in your line of sight, then would you see a shadow at all?
You should, because what will happen is that there will be, so this picture is basically what you see in the so-called, what is this movie called? Interstellar picture. So you're looking at the plane of the accretion disk, but what will happen is that there will be bending of light, and some of the lights will, even the behind, there will be lights coming towards you. So what you will see is a flat and then little bit of light on the top of it. This is exactly the what is movie called? Interstellar picture.
Okay.
Now think of it that your line of sight is from this, you're going on theta equal to 0. Okay. From theta equal to 90 degree. So the black hole you see at 87, M87 is supposedly at theta equal to 17 degree. So you can think of, you're looking at like this. So this is the picture you're looking at like this.
Sorry. Oh, so it's almost.
No. It's rather, this is theta equal to 0. This is theta equal to 17 degree. So
okay, so it's almost like this.
Almost like this, exactly.
Okay, fine.
So you are looking from the, let's say, accretion disk is equator, then you're looking from near the pole, right?
I'm 17 degrees. So pole is at, theta is measured from the pole. So theta is 0 at the pole and pole is at around, so the modeling says you are at the around 17 point something degree.
I'm sorry, Sudipta, is it like this or like this?
I mean, that I don't know. I have to look at it. Exactly. I don't know. I mean, what I mean to say, this, or I'm looking at, is that what you're saying? Or?
I mean, is the accretion disk leaving a hole in your line of sight or not?
The accretion disk, the center is a black hole, right? I mean, if you believe in the standard stuff.
Yeah, no, but suppose I've got an accretion disk at, let's say, 3M.
Okay.
Okay, now there are two possibilities, right? One, the accretion disk surrounds the black hole from your point of view, from your line of sight.
Okay.
Another one is that there's some part of the accretion disk in front of the black hole from your line of sight.
I think what is happening is the first possibility.
Yeah,
but but I'm not very sure. Okay.
Thank you.
That is the theta that he was talking about.
Yes.
No, I thought he was talking about the theta with the plane.
So there is a theta.
Plane of the accretion disk.
This is a plane of the accretion disk. What I mean, plane is the plane of the accretion disk. Okay. Accretion disk is more or less at that theta equal to 90 degrees, the equatorial plane. Because of the symmetry.
Okay, fine. Yeah, okay, thank you.
And we are watching from 17, so almost
17.
from the pole.
Almost pole, yeah.
So almost seeing a circle, you're saying.
Yeah.
Almost seeing the circle, but remember there is a gravitational light. Hello?
Yeah.
Yeah.
Hello?
We can hear you, sir.
Hello? Can
Hello.
you hear me?
Yes.
Yeah.
I think you broke off.
Maybe he lost us. But I still don't understand, why can't there be any accreting matter in front of the black hole? So that, is he saying that that's not happening in this case?
I think first he's saying A, that's not happening in this case. And B, I think he's saying that even if it were happening in this case, you'd still see some contrast between front and back, because the stuff at the back will not come to you from that angle. So you'll only see the stuff in the front, not the stuff at the back.
So I can distinguish still.
Still, probably the ratio, this 10:1 will go to something smaller, maybe 3:1. I mean, not that I know anything about it.
Right.
But it seems like this is particularly favorable, right? That the accretion disk is that way, so that it doesn't obscure the shadow.
Why?
Sorry, how big is this accretion disk compared to this?
Well, certainly more than this, because all orbits smaller than this are unstable.
Okay.
Roughly speaking, the model of accretion is that it accretes outside this unstable region.
I see. And in the case where this light ring is stable, I mean, I don't understand how can it be stable.
Yeah,
So,
I didn't understand that either. I think he'll come to that. I mean, yeah, maybe the stable. Yeah, I don't know.
then you will have many light, a lot of light coming in. I don't understand.
Yeah,
Many-
yeah. It then doesn't seem like a boundary anymore. It seems like something else. I suppose that's the main, a lot of the point of his talk.
Mhm.
So I have a question, like what happens when you have RO equals 2.1 m? I mean, according to his diagram, you have a certain angular part which is bright and the rest of it is dark. So what do you see in that case in the telescope?
That means very close, right? Very close, you will see almost everything black. I think.
Yeah, you'd have to
I
look.
see. So that's just that's just saying how bright it is it? I mean,
They say what angle you
part
get
of-
any light from. Assume you've just got background light coming. There's over a certain region you see nothing, and then from some angle on you see something. And he's telling you what angle you'll have to put your telescope very high to see anything.
So as we go close
so
to the light ring, you will start seeing black region extend to half the sky, right?
Half the sky, I was wondering if it could be even.
Yeah, in the picture it seemed like full sky, but should it not be half the sky because you're going tangent to this, and then suddenly it becomes dark or something? I don't know.
It could be that light bends so much that it goes around and comes back to you.
Hi, Shiraj. Sorry, there's some.
Yeah, sorry. Please continue.
Sorry, there's a connection. There is some problem, but I think I've connected through my Wi-Fi now. Okay, good. So now let's go back to the issue of curve metric. What happens? So I'm not going to the details of the curve metric. So let's say look at the concrete example of the ergosphere in case of a curve metric. So curve metric is a stationary solutions of general relativity, but it has extra symmetry. It is axisymmetric. You can look at the curve metric and you see that there is no dependence on phi. Therefore, del phi is also a killing vector. The cross term, for example, this cross term dt d phi is signifies this there is a rotation in the spacetime. So, for example, you can have a zero angular momentum observer, the so-called ZAMO observer, but with non-zero angular velocity. Okay, that happens because of the existence of this cross term, and it has two isometries, killing vector del t and del phi. Del t and del phi both are obvious. Okay. So it is widely believed that curved solution represent the gravitational field of a rotating black hole outside. And this is astrophysically extremely important. Then the A is the angular momentum of the gravitational field. These are no other quantities defined at infinity. So if you look at the geometry of the curved black hole, you will immediately see there are two distinct regions. There is one region which is called ergosphere. The ergosphere is the one where the del t, that killing vectors, you have a zero norm. This is the ergosphere. So what happens? Del t zero norm means that inside del t is a space-like vector. So suppose you are outside the black hole and you want to stay static. That means you don't have any angular velocity. You are at a constant distance with the black hole. So your forward velocity will be proportional to 1, 0, 0, 0. Okay. So you can only allow to have such motion if this vector is a time-like vector. Once you're inside, the vector will be space-like. So therefore, you have no option but to rotate with the black hole. You can still have a constant distance from the black hole, but you are a stationary observer, you are rotating. That means you have both time component as well as the phi component in your 4 velocity. Or the event horizon at which there is another killing vector, which is a combination of the del t and del phi, which becomes null, and that is the surface of no return. That means, in fact, even stationary observers are not allowed inside the surface, and once you're inside, you have to fall in back. Okay, so this is the Kerr case. The Argo region is a theta dependent surface, but topologically they are all S2s, and the horizon is, you all know, the Kerr horizon, which is at external horizon m equal to m plus square root of m square minus a square. Okay, so this is the structure of the space-time for Kerr black hole. So Kerr black hole, it is rather difficult to define the notion of the light ring and the shadow, but you can do it. Okay, but I will only talk about the equatorial plane because this is easy. Because in equatorial plane, if there is a null geodesic, it will stay in that null geodesic in that same plane. So this alpha and beta are exactly some coordinates by which I am describing the motion of this null geodesic, and A is the ratio of J by M, and you clearly see that when A is 0, it's again a sphere, and which is as expected for the Schwarzschild case. But with the increase of the A and the maximum value of A is allowed is 1. After A is equal to 1, it's no longer a black hole, it's a naked singularity. And you can see that the shape of the shadow on the equatorial, I should not say shadow, the light ring in the equatorial plane, and there is a deformation. And this is exactly what is happening for the rotation.
Sorry, I haven't understood. What is A?
A is the angular momentum, J by M.
J by M, I see. And what were this beta and alpha? Sorry.
So you in the equatorial plane, you want to show the trajectory of the light ring in the equatorial plane. So you introduce certain coordinates in this plane, and you write down the contour of this light ring, the motion of this light ring in that equatorial plane. So I am at the plane theta equal to pi by 2. This alpha and beta is thus coordinates. Okay. So if it is a Schwarzschild case, it will be like alpha square plus beta square equal to 1, or some constant will be the ratio of the A equal to 0.
Okay. So if this is the equatorial plane, then there should be some symmetry, right?
Exactly. So equatorial plane. So this Kerr black, this is exactly why in equatorial plane is very special case for Kerr black hole. What happens is that Kerr black hole has a Z2 symmetry. So around theta equal to pi by 2 and below theta equal to pi by 2, there is a reflection symmetry. And this is why at theta equal to pi by 2, if you put null geodesic, they stay there. But this is not true for any other plane. Any other plane, the null geodesics will actually move on a 3D, it will not confine in a single plane.
So, but this plane that you're drawing, that's the equatorial plane.
That's the equatorial plane.
But why is there no, okay, so they may stay there, but why is there no symmetry? Why is the red guy looks kind of asymmetric?
That symmetry is gone because it's no longer spherically symmetric.
Okay.
Okay. The circular nature is gone because there is a this is cross terms actually is responsible for this.
But I thought just the SO2 rotation is there, right? Or not?
Let's see. I mean, on the equatorial plane, yes, but there is SO2 on the equatorial plane. I have to think about it. I don't know, but this symmetry is, the shape is definitely distorted. So maybe there is a symmetry on the axis of the equatorial plane, but there is no symmetry on an axis on the equatorial plane. So this shape is gone because of the rotation.
Sorry, is there a simple relationship between the alpha beta coordinates and the R phi coordinates, or is it too complicated?
No, I don't think there's a trivial relationship.
Okay.
Good.
I was wondering something.
Yeah.
By equatorial, you mean if the rotation is on the z-axis, equatorial, you mean the xy plane?
No, I mean the theta equal to pi by 2 plane in the usual Boyle linguistic coordinate.
Isn't that the xy plane? I mean the plane perpendicular to the rotation.
If z-axis is the rotation, then it is the xy plane.
Okay. So yeah. So I had the same question as Abhijit and I think and I was wondering whether your coordinates are somehow breaking the symmetry. I mean, it seems to me that as Abhijit said, that SO2 rotation should not. There's no special.
What will be the axis of this SO2 rotation?
Z-axis.
Z-axis. So
yeah, along the origin here.
Yeah, I see what you are saying. Okay. I'm not sure. I have to think about it. I don't know.
It may be something to do with the coordinates.
It may be, I doubt actually, Shiraj, because these are, I mean, oh, you're saying that because in this alpha beta coordinate space, they looks like this curves.
Exactly. If you just write down the d by d,
maybe
the killing vector.
Oh, yeah.
Yeah.
I see what you're saying. Could be, but I have to check. I can't give you.
What is the logic behind these alpha beta coordinates again?
This is just, you want to coordinate it. And it looks simple because, and also there's a clear analogy with Schwarzschild case where alpha square plus beta square equal to 1. That's all, just a choice.
Okay. And R phi is no good somehow?
No, you can write. I mean,
Okay.
You can do
It's just a way to represent. All right, fine. Thank you.
Okay. So as I was emphasizing that light ring does not automatically imply that the central object is a black hole. For example, there are exact solutions. Examples for exact solution do not establish that the existence of light ring. I mean, you could have, just by looking at light ring, you cannot come to a conclusion that you are looking at a black hole.
Yeah. Sorry, one quick question about the Kerr black hole. Again, if you just send light from infinity,
okay,
and once again ask what does an observer very far away see, once again we will get some sort of shadow region, right?
Yes, you do, but you have to be a little careful. What happens is that when you look at, you don't have, you are not looking at the equatorial plane. You can be in arbitrary direction.
Yes.
Then there are these light regions where the spherical null geodesic moves. Okay. Because in any other plane, the spherical null geodesic will not be confined to a single plane. They will move around. So then what you have to do is that you have to write down your line of sight and how they're intersecting with these light regions. And that will ultimately determine the shape of the shadow.
Fine. But it will still be one contiguous shadow, right? One region with some funny shape.
Yes.
Okay, fine. Thank you.
But thanks for asking, Shiraj. But for Kerr case, there is a very special, I mean, the light regions are connected. That is why you are getting a continuous shadow. There is no general reason, at least I don't know, at least you can't prove that in general, the light regions will have to be connected. So for any, arbitrary metric, you could have a disjoint light regions. Then the shadow will be not continuous. So I should point out that.
Yeah.
Sorry, one more question, perhaps along the same lines. So in the Schwarzschild case, I can see why is it that the light ring should determine what the shadow is. But in this case, the light ring is about what is happening in that plane, in the plane, where you are considering the light.
Yes.
Right. But the shadow is about the orbit of light which is transverse to it.
Yes.
And that may be different, right? Because you don't have any spherical symmetry.
Yes, so, I agree.
For example, this equatorial, if I'm looking from the pole and we are seeing the equatorial orbit of this shape that you drew, that need not be the shape of the shadow.
That did not be at all at the shape of the shadow. Absolutely.
Okay.
So let me ask you this question: that how do I so here I have a general solution. I can write down the potential. I can look at the.
Sorry, I have a question.
Yeah. Yes.
Could you go back to the previous slide, please?
Yeah.
Yeah. So A equals 0.99 means J equals M almost, right?
Almost J equal to M. Yeah.
So are you saying that for J equals M, the light ring assumes that red shape?
No, the red shape is, for almost extremal black hole, that is the shape. Almost extremal.
So this is a theoretical derivation, right?
This is from the metric, that's all.
Yeah. So
this is just from the metric.
So then what happens to the SO2 symmetry as was being pointed out?
I agree. This is the question. So I don't have an exact answer now. So as Siraj has pointed out, it could be the choice of the coordinates is making them deform. But if I look at the R phi coordinate, maybe the symmetry will be restored. I have to look at it.
No. R phi coordinate in the sense, okay, so when you look directly at the black hole, you'll just have so in the R phi coordinate, in the R phi coordinate should be a circle, but in this alpha, how are the alpha and beta related to the R and phi?
They are related to R phi coordinate by a complicated coordinate transformations, so that I can project it on a plane.
Maybe that is the reason.
That is, I think, is a reason, but I'm not sure. I have to look at it. Okay, I can't give you a 100% answer. It seems to be a reasonable. Okay, yeah. Okay, so how do I define a general? First of all, I have to define a general stationary spacetime, and that is not easy to say because it's, so I will look at a very subclass of it. I will assume that I am looking at a spacetime which is stationary. So there is a time-lag killing vector as well as a axial killing vector. That means it's a stationary as well as axisymmetric. Okay. So please note that the existence of the second space-like killing vector, the axisymmetry is a crucial assumption. I cannot do this calculation without this assumption. So not only that, this is not even the general stationary spacetime. The general stationary spacetime will have all possible terms, all possible cross term in a given coordinate system. Okay. So this is what relativists called a circular stationary spacetime. It simply speaking is that certain cross component, I can always choose coordinate system for which certain cross components are 0, and I will be able to bring the metric into this form where there is only cross component in t and phi in Boyle linguistic type coordinates. This is never guaranteed in general. Okay. But it turns out there are strong theorems in general relativity. If I'm looking at a vacuum stationary axisymmetric solutions of Einstein's equation, that means RAB equal to 0, then it is guaranteed that I will be always able to bring the solution into this form. And this is what is called the circularity theorem. Okay. In fact, recently there is a paper by Yunes and their collaborator. What they have shown is that, okay, if it is true for general relativity, any theory of gravity for which it is perturbatively connected to general relativity, that means there is a Taylor expansion around general relativity, it is guaranteed that if you start with a circular solution, the solution of that arbitrary theory will also be circular. Okay, this is a very, very important theorem because it tells you even if there is a corrections to general relativity, even there are modifications to general relativity, as long as they are small, small means they are Taylor expandable around general relativity, the metric is Taylor expandable, it is always possible to work with circular metric. Okay, so that's a important. So therefore, I will consider this form of metric for the analysis. Okay, otherwise, I don't know how to do that.
Sudipta, I didn't quite get what's circularity.
Okay, so the definition, the technical definition would be there are certain kind of integratability of the two planes. So basically, given a stationary axisymmetric metric, there could, if you use a Boyle linguistic type coordinate, there could be all possible cross terms in the metric, right? You can have a cross term in TR, let's say. So the circularity tells you that if the Einstein's equations are satisfied, RAB equal to 0, it is always possible to find certain integrability conditions to be satisfied so that these cross terms can be set to 0 in a given coordinate system. The matrix simplifies into this form. This is what is called the circularity theorem.
Nice. Okay.
So, and this is an important theorem because what happens, for example, this is only true when Einstein's equations are true. But what if Einstein's equations are not true? There is some corrections to Einstein's equation. What has been shown is that even if there are corrections, as long as these corrections are Taylor expandable around Einstein's equations, this criteria will be true order by order. So basically, if the violations from Einstein's equation is order alpha, let's say some parameter alpha, then the violations from circularity at that order will be alpha square. This is what is proven by Yunes. So therefore, you can safely take, as long as you believe that there is a metric theory of gravity, you can safely take stationary axisymmetric solutions to be circular. That's the point.
I see. So basically, if you have some DTDR term, and if you want to get rid of it, then you have to make a coordinate transformation. So that will give you some differential equations. So you may or may not be able to solve those differential equations.
And it turns out if if RAB is 0, you will be always able to find such coordinate systems.
I see. And then if it is, let's say, some higher curvature corrections, then you can always solve these differential equations order by order.
So it turns out that if the violation, if the general, suppose you look at GAB as the solution of general relativity and order alpha corrections to the general relativity solution, then the violation of circularity, you can always show it will be at order alpha square.
I see.
So therefore, order by order, you can work with this circularity.
Okay. Thank you.
Okay. So
So is there any way of seeing such deviations, such order alpha deviations from what is being seen?
I mean, you mean the order alpha deviation of general relativity?
No, I mean, in whatever you're seeing in the data, is there any way of sort of discerning whether there are any order alpha deviations from general relativity? Yeah, for instance.
So, although this is not related to what I'm saying, I'm just talking about a theoretical theorem. But in principle, you can use the shadow to test whether curved black hole is the correct solutions or not. If it turns out curved black hole is not the correct solutions, then you can model that extra part by using order alpha corrections to general relativity.
But would that mean that you're then seeing signatures of corrections to general relativity?
Well, if general relativity is correct, the black hole solutions, the uniqueness theorems, everything suggests the black hole solutions we should see should be curved. And if we don't see curve, of course, it
no, you see curve, but there are some order alpha corrections.
Well, there will be a lot of degeneracy possible. You cannot say that, okay, the question is what kind of source of corrections these are. This one of the source could be higher curvature terms. There could be some non-minimal coupling, some other matter field which we don't know. I mean, breaking the degeneracy will be next to impossible. You know what I mean?
There's no way of figuring out whether there are any higher order corrections to GR from all this. That's what you're saying.
Well, I would not make that comment. Ideally, yes. And in fact, if you look at the recent papers in what they have, the collaborations, they do have modeled and shown that what kind of constraints, given a model, what kind of constraint the model parameter has from the EHT observations. But these constraints are rather weak.
Okay.
That's the right statement, I would say. Okay.
Okay.
Good. So what is ergosphere? So in this coordinates, in this metric, in this form of metric, there is a killing vector del t. So I can safely define the ergosphere. And if you define the ergosphere will be somewhere GTT equal to 0. This is where the norm of the time-like killing vector vanishes. And you assume that this is some r as a function of theta. I will assume the asymptotic flatness, although this can be relaxed, but I will assume it asymptotically flatness. That means I will assume that there exists some fall off conditions at infinity, which is of this form. With these assumptions, now I'm going to define the light ring. Okay, how do I define the light ring? Remember the light ring, the definition of the light ring was a circular null geodesic. In that hindsight, this is what the light ring has been defined. It's a null geodesic with a tangent vector field. Okay. Give me a second, there is some problem with my, okay. So it's a null geodesic with a tangent vector field that is always a linear combinations of the vector fields del t and del phi. So you can clearly see once I define the light ring in this way, it immediately means that the tangent vector to this curve is only along the direction of del t, that is obvious, but also along the direction of del phi only. That means in terms of photon momentum, the r and theta component of the momentum and the derivatives are 0. That means it's a light ring. Okay. So this is the definition of the light ring with which it is being defined for this general stationary spacetime. It will obviously match for Schwarzschild or the curve case. Okay. So this is only the curve. I'm not talking about whether it's a stable or whether it's a minima or the maximum of the potential. Okay. So this light ring defined in this way can be both stable and unstable. Good. So let's go ahead. Sorry. Now I have to define what is called an ultra-compact object. So far I've been a little bit, not very precise. So I define a compact object with an ergo region, not necessarily a black hole. A black hole is also an ultra-compact object, but not all ultra-compact objects have black hole. Then there are recent, very interesting results, very recent results, particularly from this group in Portugal.
Sorry. You said your light ring was a linear combination of dt and d phi, right?
Yes.
Now,
and null.
But one could imagine something a little more complicated, moving also in the theta direction.
Yes, exactly, Shiraj. And I will call them as spherical null geodesic in analogy in the curve metric. In curve metric, there is a light ring on the equatorial plane, And that is exactly what I was defined. But if you have, for example, you may say, what if I have a del theta term?
Yeah.
So curve which, so that I will call a spherical null geodesics.
Okay, fine. Thank you.
Okay. And whether they exist or not is a separate question in a given spacetime. But now I will only talk about the light ring. Okay. So there is a paper which by Cunha, Pedro Cunha and Hedro and Barty in their group, and this group is very active in understanding the properties of the light ring. What they have shown is that if there exists an ultra-compact object which is not a black hole, okay, there is no horizon, they show that if they have one light ring, that is the assumption, if they have one light ring, there must be another light ring. So if there is no horizon, the claim is that light ring will always come in pairs. Okay. That means if there is one maxima and minima, there should be another maxima and minima. Okay. And the argument they use is a very interesting argument. It's a remarkably topological argument. And not more than that, there is a second part of the argument, which is extremely important. What they show that among this pair, one of them has to be a stable light ring. So let me again repeat, because this is important. What their paper starting assumption is that you have an ultra compact object that there is no horizon, but it is compact enough to have a light ring. Next assumption is that there is one light ring. Then the claim is that you can show there must be another one. Not only that, you can also show that one of them has to be a stable. That means minimum of the potential. Yeah, Shiraj, you have a question.
Roughly, I'm imagining the first, just to understand, I'm imagining that if there's no horizon, then every light ray that comes from infinity has to come out, right? Where else can it go? Unless it sticks in your light ring. If it stays in one ring, fine. But if it starts going inwards, it has to come back out because there's no other asymptotic region.
Yes, okay, yeah.
So in this case, it seems to me that the light ring has nothing to do with the shadow. Is this correct?
I mean, let's see. So so you look at the solutions of the null geodesic outside this object. So assuming some kind of basis theorem, the outside null geodesics have no idea whether they're moving in a black hole spacetime or you say a spacetime which does not have a horizon.
Yes.
So therefore, in that sense, the structure of the picture, which I shown for Schwarzschild, will be identical for this object.
Are you assuming that if the null ray hits the object, it gets absorbed?
That is never used in this kind of argument, because what happens, what you actually look at only the background structure and the metric. But I see what you're saying. You're saying that what should I see in terms of the light once got into it? It either scatter back to me or it get absorbed.
Right. I mean, if you're just following light rays, I think it has to come out to infinity, because where else can it go?
But okay, so in that case, one has to model how this light ring goes into the object and whether it is absorbed or not.
Right. So
that answer is not given in these calculations.
I think, but if you suppose in this calculation you don't take into account absorption, then the calculation would have to tell you that there's no shadow. Because if you're just
calculation, okay, but calculation does not even talk about shadow. The calculation simply talk about the light existence of the light ring.
Okay, good. But I'm saying that suppose you extended this calculation to one dealing with shadows, you would think that it would have to follow that the light ring has nothing to do with the shadow, because it can't be a boundary between those that come out and those.
I agree what you are saying. I agree because there is no horizon. Where would the light go?
Yeah.
I could be possible. Okay.
Okay.
Actually, this confuses me. I'm confused as to how can the light ring exist if the impact parameter is less than that of that forms the light ring, then it should not come to me, right? It should
no, but light ring, the question of light ring existence is that is there a circular null geodesic allowed by the metric? Or circular means, I mean, R as a function of phi only, okay?
Yeah.
Is there a null geodesic whose tangent vector field is only linear combination of del t and del phi? Is it allowed by the metric? That is the question of the light ring.
Oh, right. It's not like a light comes and
yeah.
Okay, fine.
What Shiraj is asking, how do I see it, this object in the sky?
Yeah.
Okay. So I will little bit talk
So
about.
I have a question. I have a
Yes.
naive question.
Yeah, please.
So this light ring, you're saying that this light ring is essentially governed by the killing vectors del t and del phi.
Yeah.
Right.
Hmm.
So
In fact, that is why I need the
light,
killing vector.
yeah. So essentially the light governed by these the light rays governed by these killing vectors would go around the light rays, right?
Well, what I mean to say is that if this curve exists, if there exists a null geodesic whose tangent vectors are only combination of del t and del phi. Let's think of a short shell. It will be a circular null geodesic.
Right.
Because in spatial, it will be closed, because spatial orbits are the orbits of del phi, which is closed. And of course, in time, it will be evolving. So in space-time diagram, it will be like this. It is evolving.
Right. So it will be a spiral. It will be a spiral.
Spiral. Evolving in the direction of time.
Yeah.
It's a spatially closed orbit.
In a spatially closed orbit. Now, I guess this question has been asked again, and I'm asking it again. How do you see this light? I mean, because if it's going around in spirals, how does it come outside and
you don't see this kite. This light is just a boundary of one surface. What you see is that to construct the shadow, you have to illuminate. First, you have to figure it out whether this light ring exists or not. So this light ring will be in one plane. Then you have to illuminate the object with lights from the behind, and then study, given this light ring, how this object light rays are deformed towards you and projected in the background sky. Then what you get is a shadow. So that has not been done anywhere. Hello? Hi.
Sorry, you got your connection was a bit choppy.
Yeah. So what I'm saying is that to construct the shadow is a next order question. Given this light ring, if it at all exists, you have to study how the background light now is propagating in this object, and then how the projections look like in the shadow of the sky. That I will call the shadow. Hello?
And why is that related to the, and how is that related to the light ring? Maybe
it may or may not be related to the light ring. It may not be related to the light ring. Agreed?
Okay.
Okay, so the existence of the light ring, now how do I, so give me a second, there is some, sorry, yeah. So if you look at now, if you demand that there exists a null geodesic, then you can show the existence of that null geodesic ultimately reduces to solution of this particular equation, where del mu h plus minus equal to 0. And where h is some kind of potential function. I'm just calling it a potential function in analogy with the, the Schwarzschild case, okay? And this is given by the complicated combination of the metric and the components of the metric. For h plus and h minus, these are just telling you there are two sense of rotation, plus rotation and the clockwise rotation and the anti-clockwise rotation. So the question is, given this equation, if there is always a solution of this equation, there exists some RL and theta L satisfying these equations outside the ergosphere or the object, then I will call there exists a light ring. Okay, so that's the light ring equations. This is like saying whether the potential has a maxima or minima. Good. So a light ring can either be a local maximum of h plus plus, or it could also be a saddle point. And then what they do in their paper, in Kuna's paper, what they do, they use as a topological argument. So they define some kind of topological quantity, what is called the Brewster angle. And they prove that this Brewster angle must be invariant. And they show that in that sense, if there is one light ring that adds one value to the Brewster angle, there has to be another light ring to make the Brewster angle to be invariant. So basically the total Brewster angle turns out to be 0. And then if there is one light ring, it adds a charge, topological charge of +1, then another light ring must be there to make a topological charge of -1, so that there is no violation of this topological invariance. So this is a rather complicated argument, and not only that, this argument requires Einstein's equations, null energy conditions, but in that, at the end of the day, what it shows is that if there is no horizon, there must be a stable light ring. So that means there has to be a stable light ring, means if you remember the minima of the potential. The Schwarzschild light ring was a maximum of the potential, okay? And then the claim is that Schwarzschild light ring, this stable light ring is bad.
Sorry, and could the stable light ring be going inside, to be contained inside the matter?
It could contain inside the matter also. That depends on the detailed modeling.
Okay. And then how can we know whether something is good or bad unless we know what the equation of motion of the matter is?
Okay, so what happens is, you mean the equation of state of the matter, right?
Yeah, I mean, we have to, the whole thing will evolve together.
Yes.
So unless we
So
say
what
something about
happens?
matter.
Exactly. So this analysis is actually done. What is done is that this is exactly is done in the next page by Cardoso, and it's actually long ago of this proof. Okay. What they do is that they consider a model of a reasonable boson star where the energy equation of states are known and there is an exact solution in that equation of state. And you know there is a minimum of the potential as well as the maximum of the potential. In that background, they study the quasi-normal modes and also the matter perturbation, everything together. What they show is that if you start with a box phi equal to 0 equation, that phi does not decay. There is a long-lived mode. Okay. And the claim is that this long-lived mode will ultimately lead to non-linear instability. So this is the first calculations which is show. So everything has been done here. So you have taken consideration of this is an exact solution of the boson star. So therefore equation of states are known. And you look at the exact solution and study perturbations of that exact solution. They have shown as long as there is a stable light ring, that means the minima of the potential, there is always long-lived modes which does not decay. So the claim is that after some time, the first order perturbation theory will break down and there will be non-linear instability. That has not been shown in this paper, but I'll talk about a recent paper which actually shown that this has happened. And then there is a question, what is the time scale of this instability? Is the time scale longer than the Hubble's time scale or is it very small? So there's a recent paper which says indeed the time scale is short enough for these objects to be destroyed.
And any idea what the endpoint of this instability is?
There are two claims. One endpoint is that this, this is answered in a paper which came actually 3 days ago. So I have not read it properly. But if you look at their conclusion, that most of the cases, they becomes a black hole. At the end of the day, they becomes but there are possibility of rapture and others smaller point into 2-3 parts and more stresses developed and this kind of things. But most possibly they will collapse into another black hole.
That's very interesting. So basically you're saying the things that are smaller than 3m, roughly speaking,
are black holes.
Are always unstable to collapse.
Unstable collapse. That provided because of this theorem. Okay.
Yeah. Okay.
Okay. So basically if there is no horizon and there is a stable light ring.
I have a question.
Yeah, please.
So this potential is in the r theta coordinates, right? I mean, it's a function of the r theta coordinates.
Okay.
Potential,
Yeah.
because that's where.
Yeah. In general, it is. Yeah. But
yeah. So
just to add, this Cardoso's work is for spherical symmetry. Yeah.
Yeah. So essentially, what you're saying is that for stable light rings, if it's at the minimum of the potential, then there's some specific r and theta for which the light ring exists. Is that the
So
statement?
light ring exists at the extremum points of the potential.
Yeah.
They
So
can be
for
minima and
instance,
maximum.
yeah. So for instance, suppose there's some r and some theta for which the light ring exists. What would that mean exactly when in the image that you're seeing? I mean, how would that get reflected
that
in
is
the
a
image?
difficult question to answer because that depends. I have to solve the full background as I was telling you. How do we translate into an image is a difficult question to answer because for Schwarzschild and Kerr, I know. If you give me a metric, I can construct this image given this light ring.
Okay, for Schwarzschild, what will you see?
So for Schwarzschild, as I described, that I will see a sphere of radius r√3 as a large distance away. 3√3m.
Radius, I mean,
sorry, not
sphere
radius,
of light.
No, in the
You mean
sky,
the
I
sphere
will
of-
see a dark patch. I will see a circle,
Okay.
dark circle of radius r equal to 3√3m.
Okay. Now, what does it mean to have theta equals some constant?
What do you mean by theta equal to constant?
I mean, your potential is your potential V of whatever potential you're minimizing under. That has two coordinates, right? R and theta. Or does it have just one dot?
Yeah. So in general, the potential will be a function of both r and theta. So it could have a saddle point also. That could be a,
Yeah.
so you have to
Yeah,
consider in both R and theta. In fact, I
Yeah.
will discuss that case in general while the derivation goes.
Okay, good.
You have a question, Somdatta? Hello. Did I miss a question? Hello.
Hello.
No. It's okay. If you are discussing what will happen, then it's okay.
Okay. So this is kind of a potential which you see, which has a minima and maxima, and these are the quasi-novel mode spectrum. Okay, it's not very important to go into detail. There are numerical calculations as well as the WQB calculations, and you can show that in the spectrum there are modes which are very long-lived mode. That means they don't decay. The time decay of the modes is not true. The Price's law in somehow is not true, and as a result, those modes may back react, and that's the claim that the nonlinear instability will destroy the black hole. Okay.
So these modes live roughly in the minimum that of your diagram, right? These modes
Yes,
live roughly.
these modes arise because there is a minima. The minima can hold it, kind of a, you can hold the perturbations in that thing.
Yeah.
That's the reason why it comes.
Yeah, thank you. And they slowly tunnel out.
In fact, that is the idea, that how long they're there.
Yeah.
So for example, this is an example of, look at the second panel, which is basically a field. Okay, or let's look at a third plan. That R equal to 0 is not very important. Look at R equal to 40 m. You're looking at the value of the field, how it is changing with time. If in general, if it is a black hole, or you know that it will sharply decay, there's this quasi-normal, there's a transient quasi-normal modes, then the field will decay. The Price's law will tell you, and then ultimately everything will be okay. The field goes down. But what happens when there is no horizon and a stable light ring, you can see that even if you wait for longer, even as 10 to the power 4 m, the field is not decaying. So these are just simulation results of the spacetimes and looking at the solutions of box phi equal to 0. The claim is, this is not shown in this paper. This is only recently claimed that this will somehow, the linear perturbation theory breaks down. There will be nonlinear instability which will back react on the system, and the system will be destroyed. So this is the simulations by Cardoso and all. Question is, what if there is it's a black hole? Okay, so it turns out on black hole there is another theorem which says that if there is a black hole, stationary black hole, obviously there is no such instability problem, but it will always have at least one light ring. That is guaranteed, as long as it's stationary axisymmetric. Of course, I have not written that. Every axisymmetric stationary black hole must have one light ring outside. Okay, so this is the status of the field when we started writing down this paper. So what we propose is this following theorem. Any stationary axisymmetric asymptotically flat spacetime in 3+1 dimension, which has an Argo region. I don't need a horizon. I need an Argo region, which have at least one light ring outside the Argo region. So that means any compact rotating object with Argo region must have a light ring. This is what we can prove. Our proof is independent of the theory of gravity, does not require any assumption about therefore, any energy conditions. It just comes from the properties of the null geodesic equation. It's actually rather simple compared to the topological argument, and we will see. Siraj, you have a question.
Yeah, you don't use equations, the gravity equation.
No. I don't use Einstein's equation.
Okay, thank you.
So therefore, that is good, but I cannot even say anything about the stability of these rings. So I can only tell you the first derivative is 0. I cannot talk about anything about the second derivative. The stability requires taking another derivative. So that's the limitations of our proof. Okay, so basically what we are saying that if you have a rotating object, as long as it has an Argo region, it must have a light ring outside. Again, light ring, I am not talking about anything about shadow or spherical null geodesic. These are second order questions. So how do we prove it? Remember that we have a light ring equation, which is del mu h plus minus equal to 0, where mu is r and theta. I have to prove that there exists a solution of this equation always just from the boundary condition outside the Argo region. That's all I have to prove. Okay? And this is the what h is, plus and minus are two senses of rotation. How do you prove that? So first of all, we look at the theta equation first, and we show that for any particular value of r, you look at any particular value, the function h must have at least one extremum. Okay. That is because there exists an axis. So this is this is given a stationary axisymmetric spacetime. It is guaranteed by a theorem by Carter that there exists an axis. That means axis, what is the definition of the axis? On which g phi phi equal to 0. And we can show that if there exists the axis is defined at theta equal to 0 and theta equal to pi, we can show that function h must vanish on the axis. So therefore, there must be a value of theta where there must be an extremum by what is called mean value or some theorem. Okay, it's calculus, I forgot the name.
And presumably this usually happens at the equator, right?
Exactly, if there is a Z2 symmetry.
Yeah.
If the curved black hole has a Z2 symmetry, therefore it exactly happens at theta equal to pi by 2. But in general, the metric, it can happen at any theta equal to theta naught. Okay. What about the radial equation? We can show that the radial equations can be written into this form, okay, where there is a L of R minus R of R, okay, where R and L are given by this complicated expression, okay. Now we use the boundary conditions. We prove that on the ergosphere, we prove that capital R function will be 0 and L will be positive. So therefore, the entire thing del R derivative will be positive. Similarly, we prove that asymptotically flatness demands, if I go to at infinity, the del R of H will change sign. So therefore, it has one sign on the ergosphere, one sign at the boundary, and immediately we'll see that it must be 0 somewhere in between. So what we will prove is that for given every theta, there exists a value of R for which del R H is 0, and the vice versa, given every R, there exists a value of theta for which del is 0. And then we can show that therefore there exists a solution for which del R theta is equal to 0. And that is exactly what our light ring is. The light ring equation must have a solution outside the ergo region. So that's the theorem. Any stationary axisymmetric asymptotically flat spacetime in 1+3 dimension so you can clearly see where the dimension part will go. Everything else will more or less remain same. Dimension part will change the fall off conditions. So you can modify it accordingly and extend the theorem to other asymptotic conditions as well as to other dimension, 1+3 dimensions. An ergo region must have at least one light ring outside. So remember that ergo region does not imply the existence of the horizon. I can think of rotating neutron star, which has rotating so fast and compact enough that it has ergo region outside, it doesn't have a horizon. Okay. But what you can show in a rather intriguing argument, which is already there. I mean, I didn't know this, we discovered it later, but it was known in the older GR book. If you look at the Kerr's paper or Carter's paper, or classic papers, if there is a horizon, there must be ergosphere. So therefore, what our proof is our proof also provides an alternative and rather simpler proof of the Kuna's result, that if there is a horizon, there must be a light ring. Okay. The important consequence of our proof is that, so remember that Kuna's proof, what it says, if I give you an ultra compact object, okay, they require one assumption, it must have one light ring. Only then they can show there must be another light ring, and one of them is stable. What we prove is that we prove that assumption. We prove that if you give me an ultra compact object which has a ergosphere, then it must have one light ring. Then Kuna's paper says that it must have another light ring, and one of them is stable. And that stable light ring is bad by the other analysis. And therefore, if there is an object with a light ring, it probably, presumably, is only possibility is that there is a horizon. Yeah, Shiraj.
So you have, do you feel you've demonstrated that neutron stars cannot have an ergosphere?
No, there are neutron stars which can have an ergosphere.
So then I didn't understand. I thought that from your theorem.
Oh, yeah. Okay. So, okay. Sorry. If you have in fact, the claim of this theorem is that no. If it has ergosphere, neutron star, there are other instabilities which will set in. There is something called ergo region instability. This is even well known before the days of. So compact object with ergo region, okay, most probably are black holes.
Okay, so I mean, we should not be able to find the neutron star in the sky that has an ergo region. That is.
Well, if you find a neutron star, I don't know how do you even come into conclusion that this is a neutron star with the ergo region. Suppose you can,
yeah,
then definitely.
LIGO detects collision of a black hole with a neutron star. We can read off the angular momentum well enough.
Perfect. And you need an ergo region. Okay. The claim is that you should not see them. If you see them, it means this instability, what you are calculating, that calculation is probably wrong, or the time scale of the instability is much higher than the cosmological time scale.
And can one repeat this calculation of the instability with, neutron star type equations of state?
Oh, good question. I wish no, I don't know how to do that. I can only suggest to you, there is a paper, in fact, I'll give you the reference at the end of the talk. There's a paper 3 days ago by Kunas and others, and we have been discussing with them also. They now have a full nonlinear simulation where they seems to suggest that indeed this happens at the nonlinear level. They are also using short, spherically symmetric case, and this result are very, very sensitive to they are doing it mostly for boson star. But with full QCD equation of state put into and doing for neutron stars, I mean, nobody has attempted it. But it's important to be done.
Thank you.
Good.
I have a question.
Yes, please, Abhijit.
Like, so are you saying that the solutions have are functions of some specific r and theta, but for some specific r, you can have only a specific theta? Is that correct?
So the light ring is a curve.
Yeah. So it's a curve,
which is a function of r and theta. Yeah.
Yeah. No. See, it's a, first of all, it's a the light ring, as has been pointed out before, the light ring is a curve in the r phi plane, right?
Yes. Yeah.
R phi plane. Yeah.
No.
Now,
in this case, yeah, it's a function of r as a function of theta. There is no phi dependence.
Yeah. So this when you have a specific r, you're saying that according to your equations, you can have only a specific theta. Is that correct?
On the light ring, yes, you are correct. On the light ring.
On the light ring.
So what I'm showing.
Does that?
Yeah, please.
What does that mean? What does that mean for the shape of the light ring? I mean.
Oh,
so
no.
Does that mean that?
It just only means a spatially closed curve. The shape depends on the details of the metric. Shape would depends on the details of the shape, area, and all those things. More than shape, let's call it how it is different from the area of a black hole. Okay, sorry, a circle. Okay, that depends.
No, for instance, could it mean that the light ring that you're seeing? Okay, so it's the light ring that you're seeing can be aligned only along a specific theta in the r theta plane.
So what it means is that this light ring is on a plane which is theta equal to theta naught, where del theta h is 0.
Yeah, true.
That's all.
But it's a first of all, it's a ring, and then it has to be aligned along some theta in the space-time coordinates, right?
Yes, that is exactly that.
So does that mean? Yeah. So does that mean that for a specific r which satisfies your stability conditions, you can have only a specific orientation of the light ring in along the theta direction? Is that what you're saying?
I am not able, to be honest, I'm not exactly able to pinpoint the question, but if I understand it correctly,
no. The question is, suppose you have a specific r as a solution of your equations.
Okay.
That means that you also have a specific theta corresponding to that r.
Yes. Indeed.
So does that mean that your light ring will be oriented along that theta direction?
It means the light ring is on a plane at that theta equal to theta naught.
Exactly. Yeah. But that seems to violate, say, rotational symmetry.
No, it does not. It just violates the Z2 symmetry, theta to minus theta symmetry.
Take the example of a Kerr black hole, Shomedi. Yeah. It's at theta equals pi by 2 at a particular r.
So, Kerr black hole, there is a theta to minus theta symmetry. So therefore, the light ring is exactly on theta equal to pi by 2 plane. That's all.
And at a very particular r.
That a particular r.
So there's one value, in that case, there's one value of theta, namely pi by 2, and one value of r, namely something.
And that I call. So if you change the theta, change the r, you see, there is an r theta plane curve.
Yeah.
So
So
it does not violate the
you're
physical
saying that
symmetry.
there is no symmetry along the theta direction. Is that what you're saying?
I mean, in general,
The
need not
symmetry
be,
along
right?
the theta direction is violated.
In general, need not be, right? It's an axisymmetric metric. It has a Killing vector del phi and del t.
Yeah, there's rotation around the z-axis.
There is a reduced axisymmetric. There is no SO3. There is no SO3
Okay.
in this metric. Well, there is SO3 for Schwarzschild.
Okay, so then the follow-up question would be, if the light ring is at all related to what we see in the sky, then why do we always see a certain shadow? Why do we always see what we see? I mean, if
Okay, the shadow is a much more complicated thing. Let me emphasize this again. Light ring questions is a question which I'm writing here, but to see the shadow again, there are other things you have to consider. Given the space-time with the light ring, even for curved black holes, for example, the equatorial plane does not determine what you're going to see. Is that clear? So equatorial plane is not going to determine what you're going to see. What you're going to see is that what is your angle, and at which what is your line of sight. And there are, for example, photon regions in curved space-time. Okay. Is that okay? Should I go ahead?
So Sudipta,
in the sense that I mean, do you expect to see this sort of shadow for all sorts of whatever black hole that you image, or whatever thing that you image? Do you expect to see exactly this sort of shadow, or do you expect to see other things as well, depending on your analysis?
That's a difficult question to answer, but let me answer certain kinds of analysis which we did. If the metric is almost curve-like, that means it's curve plus certain corrections. Okay, you can show that you will see the same thing. But if there is a widely different object, for example, if there is no Carter constant at all, okay, I can't even reduce the system into first order differential equation. I don't even know how to see anything.
So it doesn't depend on the equatorial plane of the curved black hole, right? I mean, the curve.
It does not. The
plane of the curved black hole could be anyway. Is that right?
No, rather given the equatorial plane, your orientation could be anywhere. I think that's the right.
That's what I'm saying. Yeah.
That's
yeah.
Right.
Okay.
So
thanks.
One quick question. So this theta business, that there could be a light ring at any value of theta, not just at pi by 2, but any value of theta. Right? It's a bit confusing because, I mean, naively speaking, this centripetal force, I mean, you seem to fall down, right? Because of attraction. There is no. Sorry.
Why would it fall down? I mean,
towards the plane.
So the question is that in curved black hole, theta equal to pi by 2 is a very special plane because of the theta to minus theta symmetry.
Yeah.
In general, since I'm not assuming theta to minus theta symmetry anywhere, it could possible that there exists a theta. It need not be pi by 2.
No, I'm saying, you see, the light ring defines the plane.
That defines a plane. That's a plane of the light ring, which need not be the equatorial plane always. For curve, it is.
Yeah, okay.
Okay. So let me summarize what I am trying to say. So the instability, if there exists, so combined with our work, Kuna's work and Cardoso's work, we claim that there are instabilities of the stable light ring, and this instability can actually lead to the fragmentation of the object, leading to the smaller black holes. And this is something I like to emphasize. There is a paper 3 days ago from Kuna's group, and they have actually done the full nonlinear simulation of the system. And their claim, which I have not read properly, so I have just read the abstract of this, but the claim is that indeed this is happening. And not only that, there is a far more stronger claim in the abstract that the time scale of this fragmentation is some 1,000 seconds. Okay. So therefore, if the cosmological time scale, if you see an object with, what you are seeing at the sky as an image are all black holes. Okay. So if it is not the case, we have to conclude, and this is what we call in GR community nowadays, we have developed this name, which is called this black hole hypothesis, that if there is a light ring, it implies the existence of the horizon. So there are possible extensions of our work. So as I said that one could extend our theorem to higher dimension. This is probably plausible. We use the asymptotic conditions which are asymptotically flat. We would like to know how this is generalized beyond asymptotic flat. And then it is also important, what if the spacetime is not axisymmetric? What if I don't have a del phi as a killing vector? How do I even define a light ring is not very clear to me. There is also another possibility. Note that I am always assuming circularity. Okay. This is motivated by Nikyun's paper that at least the curvature corrections don't destroy the circularity. But people have found solutions, for example, solutions in non-minimal coupling. Okay. People have shown that there are solutions, black hole solutions where circularity is violated. It is important that whether we can model the light ring and all these calculations for a non-circular metric. This is difficult. That is because the analytical or semi-analytical way you do this calculation will be completely gone. You will not be able to reduce the system of equations into first order differential equation. So what you need to do is a full ray tracing. So you actually solve the second order null geodesic equations in this background, and you have to do the full software calculation. So you have to do using a ray tracing software. This is something we are learning. We are learning from the in collaboration of few friends who are in the black hole collaboration in the AHT team. We're learning how to actually do the ray tracing in this background. And it will be very interesting if we can actually find out how the ray tracing gives the pictures for a non-circular spacetime. Thank you.
Let's thank Sudipta once. Are there any questions?
I had a quick question.
Yes.
So is maybe slightly vague, but in the holography/ADS CFT context, is there some simple interpretation for the kind of light rings that you're studying? And if so, then can you translate the black hole hypothesis question to some question in CFT and study it there?
Well, that will be a very difficult question. You have asked me a really difficult question. But I know one paper, which I'm not able to recall the results, which actually looks at that is there a signature of existence of this light ring in the dual ADS plasma. I don't remember the reference. I'll dig. I don't even remember. It's long ago I have seen it. Okay. So I don't know in terms of states. See, horizon is a thermal state. That is easy to understand. But if there is no horizon, I mean, I don't know. I mean, so basic. Okay, if we believe in ADS CFT, and if we believe that, okay, this audience, everybody probably believes in ADS CFT, but then the claim will be that if this instability exists in ADS, by the way, that has to be checked. Okay, nobody has checked it. Then I would presumably say that the states which dual to this geometry will have some pathology. I don't know what kind of pathology. Okay,
right.
Be my guess. But beyond that, I am not literate enough to comment on ADS CFT.
No, great. Thank you so much. Thank you.
I also had one question. In this Kuma's proof, where they prove that these light rings are coming in pairs, do they use Einstein equations, or it's also for any general?
So there are two parts of that proof. If you want to prove that given a light ring, it always come as a light ring, another light ring, that does not require Einstein's equation. Okay, that just come from the what is called there's a Brewster topological invariant omega, the invariance of that part. So basic idea is that at the flat spacetime, W is 0. This Brewster invariant topological invariant is 0. So if you form a light ring through a gravitational collapse, their claim is that it should be 0 all the time. So they show that if there is a light ring, the way these Brewster angles are defined, they're defined through a contour integral center spacetime. As always, these are topological invariant. Existence of light ring puts a topological charge of +1. So therefore, there must be another contribution -1. That's the claim. Okay. This part does not require Einstein's equation, but you need to also, they could able to infer also the stability of this light ring. What they show that if now you use Einstein's equation along with null energy condition, this light ring has to be stable, at least one of the light rings. So that requires to find the sign of the second derivative of the potential. And second derivative of the potential, you can clearly see it's the second derivative of the metric component. and therefore it is related to the curvature. That is why you need to use the Einstein's equation. It will be actually quite interesting if people find that whether this is true. Let's say even for theoretically, is it true for R square correction or RAB correction, whether their theorem goes through? I don't know.
Are there any more questions?
I have a question. Like in your starting transparency slides, you had something. You had a statement about naked singularity. So, is there any way anything can be said about naked singularities?
Well, I added that as a possible alternative, but in my personal opinion, they are a little bit more exotic, because if there is a naked singularity, they are highly quantum gravitational object. Okay, I mean, at least the way I understand naked singularity, then I don't even know what does it mean observing them and doing classical GR analysis, ray kind of analysis. So I'll be very careful in working with naked singularities. That's all I can say. But there are people who actually construct shadows of naked singularities. Okay, I'm not sure that that is a very well-defined object, given these objects are, highly gravitational, quantum gravitational object, presumably, and I am exchanging light rays with them. I don't even know what happens to the predictivity and all those things.
Well, why are you saying that they're necessarily quantum gravitational?
No, I'm not saying they are, but if it is a very high curvature region, I would expect that quantum gravitational effects will be very important near the naked singularity. And if they are naked, then I am exchanging information with them. So in my cautious slice, there's a light coming from the singularity to me. I mean, how do I evolve the data after that? I don't know, because the classical analysis breaks down. But you may
And the second question is, how do you kind of relate all that you have done to what is being seen? As you have said that this is just what you have done is just.
Actually, to convert what I should see is a question of constructing the shadow. Okay, this is already done. It's not that people have not done it. Okay, that requires construction of the shadow. If you have any theory and if you have null geodesic equations in that background, you could be able to actually construct how do you see, just by solving the null geodesic equation with respect to a background screen and projecting it on the background. But there are complications. Let me again point out, because there is accretion features. Okay, so that accretion feature, how do you add? Okay, that is a black box, at least to people like me. That is there with the collaboration. They have the ability to understand how the accretion features changes the features in the thing. Okay, so that part is not clear. That is a complicated.
Could it be that the accretion disk, I mean the image of the accretion disk is much too dim compared to the shadow or the outer ring that is being seen?
I think the conclusion, the belief is the other way around. The accretion disk has a lot of processes which can contribute to the radiation. I think it's the other way around.
So then why what is being seen is not being attributed to the accretion disk?
It is attributed to that. It is, that's why I'm saying that the modeling uses the parameters of the accretion disk. So what you do?
But in that case, the accretion disk could be in any plane, right? I mean, why do we always
but this is why so M87, for example, in M87 we have the X-ray observations. Okay, let's say I ask you that how do I know that M87? Let's little bit more. Let me phrase the question a little bit more. Can I fit the M87 data with the boson star configuration? Answer is yes. The image data you can fit with a boson star configuration, but it will be in contradiction with the X-ray data. There are jets in M87, so that definitely defines you the plane of the accretion. You have already seen the jets in M87.
Sorry, just one comment. Maybe we can wrap the discussion up, because the lunch time is also getting close. No, not. I mean, Somdatta, is that okay?
Yeah,
maybe
absolutely.
you can write to him.
Definitely.
Thanks a lot, Sudipta. It was a wonderful talk.
Yeah,
Thank you.
Sudipta, great. Thank you so
Great
much.
talk.
Thank you.
Very clear.
Thanks.
Very illuminating. It's not the
Thank
kind of stuff we get to hear.
Yeah.
Thank you. Thanks a lot. Bye.
Thanks.
Yeah.
Thank you, sir.
Yeah, very clear talk. Very
Bye-bye.
nice. Thanks a lot.
See you.